Yeah. So can you see my screen, Srijit?
Yeah, it's perfect. It's perfect.
Okay. So thanks, Srijit, for the invitation to speak here. And I'm going to be speaking about recent developments in semi-classical gravity. So I just like to warn the people who are listening that it is going to be technical, but the problem is those recent developments are very technical and there is no way around it. If I have to explain what they are, I'll try to be pedagogical, but I will have to get into some very technical details. Okay, so let's first try to understand what is semi-classical gravity. Okay? So consider quantum fields in a curved spacetime, and the quantum fields have some energy momentum tensor TAB. You could have gravitons also as part of these quantum fields. So you could think of small fluctuations of this curved spacetime as just gravitons. And that will be included in the TAB. Then the back reaction on the spacetime is governed by the following equation. Okay, so if you cannot see my pointer, then let me just tell you that the left-hand side is the Einstein tensor for the space-time. And the right-hand side, the source is the expectation value of the energy momentum tensor in some state of the QFT. So whatever state the QFT is in, you just input that in the expectation value. And this acts as the source for the back reaction on the gravitational space-time. So the metric here, let me remind you, is classical and the matter is quantum. Okay. Now, I will use the term semi-classical gravity in general for any situation in which the metric is treated as classical and the matter is treated as quantum. So, of course, we will also be explicitly using this particular semi-classical gravity equation sometimes. Now, you might wonder why I should treat the metric as classical when the matter is quantum. After all, everything should be made quantum. And indeed, there is a way to derive this semi-classical gravity limit from a full theory of quantum gravity. So these are two technical results, which I will just mention here. The first result is if you consider n scalar fields coupled to gravity with coupling proportional to 1 by n, and you take the limit that n goes to infinity, keeping n times the Newton constant fixed, then you can derive this equation. Okay, this equation some sort of pops out. This is one technical result. And the other technical result is, in quantum gravity, if I consider the one loop perturbative correction to the metric's expectation value, which is a C number. So if I consider the one loop perturbative correction to this and expand this expectation value of the metric about a background classical solution, then I again get these equations, okay, at the leading order, at the one loop order. The energy momentum tensor can also include graviton contributions. Okay, so these are the two technical scenarios in which the semi-classical gravity equations simply pop out. When we use it, we are actually, at least in the context of the point number 2, where it is derived in quantum gravity as the one loop perturbative correction to the expectation value. Okay, now where is semi-classical gravity useful? So in general, QFT in curved spacetime has been applied by Hawking to show that black holes radiate. Okay? It was done in the scenario of QFT in a classical curved spacetime. Now, the decrease of the black hole mass as a result of this Hawking radiation can be argued using the equations of semi-classical gravity. So this is the big application of semi-classical gravity. However, in this talk, I will be specifically interested in recent results that use semi-classical gravity, and this will broadly include results in which the metric is taken to be classical and the matter is taken to be quantum. Okay, so before I go into those results, let me tell you what is the plan of the talk. There is going to be two topics which I'm going to consider. One is a result called the generalized second law. Okay, it's a result which has been proven using semi-classical gravity. The other thing I'm going to talk about, if I have the time, is a conjecture, which has not yet been proved, but which many people believe to be true. So what I'm going to talk to you about is the proof of the generalized second law using some new techniques from algebra. And the hope is that these same new techniques could be used to prove the conjecture. Okay, so the topics are going to be one result and one conjecture. Okay, what is the result I want to talk about? I want to talk about a result called the generalized second law. Now, the generalized entropy was introduced by Bekenstein in the following scenario. Okay, so suppose you have a black hole and you have some matter outside the black hole. Now you throw a cup of tea into the black hole. Okay, so when you do this, you know that the cup of tea has gone inside, and therefore the thermodynamic entropy of the outside of the black hole has decreased. Okay, so simply because there is a black hole, you can decrease the thermodynamic entropy of the matter outside. In order to save the second law, Bekenstein proposed that black holes should have an entropy, okay, and that entropy should be the area of the horizon by 4G, and the combination of this black hole entropy and the entropy of the outside matter should always, so first this combination, you construct this combination, area by 4G, which is the entropy of the black hole, and the entropy of the outside matter. This sum of these two terms is called the generalized entropy. And then Bekenstein proposed that this generalized entropy never decreases in time. So it may be that when you throw the cup of tea, the outside entropy has decreased, but the area of the black hole increases and more than compensates for the decrease in the outside thermodynamic entropy. So the statement of the generalized second law is that this generalized entropy, this combination, never decreases in time. Okay. Now, this is an important statement. Can we prove it? And before we prove it, we should ask a deeper question. Okay, so what Bekenstein thought about was this S out is the thermodynamic entropy of matter outside the black hole. But what if we have quantum fields outside the black hole? Okay, then what should we take this S out to be? And it was proposed by Sorkin many years ago that this S out should be the entanglement entropy. Okay, so what is the entanglement entropy? You have a black hole interior, you have a black hole exterior. You take the density operator of your quantum field theory, and then you trace it over the inside of the black hole. Just trace over those degrees of freedom. You will get a reduced density matrix of the black hole exterior. And you take the von Neumann entropy, which is the quantum entropy associated with any density matrix, which is minus trace rho log rho. Okay, and this he proposed should be the S out, which comes in the as the second term in the generalized entropy. And then the proposal is that the area by 4G plus this entanglement entropy never decreases. Okay, the problem, although there is one problem with this entanglement entropy, it has a UV divergence. So it's actually infinite. It's formally infinite if you compute it. But there is now a lot of evidence for the following. There is a lot of evidence for the fact that the leading divergent term in this entanglement entropy can be absorbed in the renormalization of the Bayer-Newton's constant G in this formula. Okay. Now the generalized entropy is finite and contains the renormalized G. Okay. And S ent is now the finite part of the entanglement entropy. So the bottom line is there is a lot of evidence for the fact that the combination S gen of area by 4G and the entanglement entropy is finite. Although each of the individual terms has a divergence, S ent has a divergence just when you compute the entanglement entropy in quantum field theory. And area by 4G has a divergence if you think of G as the renormalized or the Bayer-Newton's constant. Okay, so the proposal is now you replace it by the renormalized G and you add the finite part of the entanglement entropy, and this result is the finite generalized entropy. Okay, so the generalized second law, which is the fact for Einstein gravity using semi-classical gravity approximation. So the semi-classical gravity equation was used in a crucial way in this proof. Now, this proof had some assumptions, okay? And there are recent developments, the ones which I'm going to talk about by Witten and collaborators, which have led to an improved understanding of the assumptions in the proof. So in a sense, we have proved the assumption, and therefore the GSL is completely, a true result in semi-classical gravity. Okay? So this is the recent development that I'm going to review. And this recent development uses lots of techniques from algebras. Okay, so let me just give you an outline of whatever it is I'm going to explain. So Witten and later these authors, Chandrasekharan, Pennington, and Witten, described something called the entropy of an algebra. Okay, so we are going to understand what is the algebra that's mentioned here and what do you mean by entropy of an algebra. Okay, so what they did was they studied the algebra of observables in the black hole exterior. Okay, and I'm going to explain all these terms. So that's the summary of the first part, which I'm going to explain. Then what they showed was that the generalized entropy of the Schwarzschild black hole at a special surface called the bifurcation surface is the same as the entropy of this algebra. So the entropy of the algebra is some statistical quantity which you get from the from doing some calculations with algebra. And they said that's the same as the generalized entropy modulo a constant. That's what they showed. And they also proved a version of the generalized second law for Einstein gravity using techniques from von Neumann algebras. Okay, so let's try to deconstruct all the terms that I've just mentioned here. Here you should now see a Penrose diagram of the complete maximally extended Schwarzschild black hole. Okay, so it has two regions, two exterior regions, the right one and the left one. Okay, so I'm going to focus on one of those two, which I call the right exterior, which I have labeled here. Okay, and what I'm going to do is I'm now going to consider quantum field theories in this spacetime. Okay, and you can consider the quantum field operators. So the quantum field, you can simply, for just illustration purposes, we can take it to be a scalar field. So here's a quantum field phi, which depends on x, right, the space-time point. So let me take the space-time point to be lying in the right exterior, in this right diamond, okay? The algebra of bounded quantum field operators in the right exterior is something which I'm going to look at, and I'm going to denote it AR0. Now, what do I mean by field operator? That also I have to define. Suppose we have a quantum field, says K phi, which is a scalar field. It depends on the space-time point x. Okay. So what I will do is I will smear it to a subregion of space-time by considering the integral. I integrate over the subregion of space-time times the function times the field, where the function f of x has support on that subregion. Okay. Why should I do this smearing? This is absolutely necessary, since otherwise this operator would have infinite norm. Okay. So what is the norm of an operator? The norm of an operator which is acting on a Hilbert space is given by norm of O is equal to, you do the following, you make O act on psi, where psi is any Hilbert space state. Then you find the norm of O psi, the usual Hilbert space norm. Okay. Multiply that by the norm of psi inverse. Okay, you take this product and you find out the state for which it is the maximum. Okay, and that maximum norm you call as the norm of this operator. Now, if you were to put, instead of O, if you were to put the field phi of x into this formula, then this formula, this norm, would turn out to be proportional to the 2-point function of the scalar field. Okay, in the limit where the 2 points coincide. And you know from quantum field theory that the 2-point function in the limit of coincidence is divergent. Okay, so this norm would actually be infinite. And this problem comes about because I'm considering the field phi of x. So in order to solve the problem, I will consider these smeared fields, which are smoothened out by integrating them over a subregion of spacetime. Okay, so this I have to do in order for the norm to be finite. Now what I'll do is I will take these functions f of x in the smearing to be having support on only the right exterior of the Schwarzschild spacetime. Okay, so they are zero everywhere else. They are only non-zero inside the right exterior. Now, if I consider these QFT operators, so all the fields which have been smeared into and have support in the right exterior region of the Schwarzschild spacetime, I am considering those QFT operators. Okay, and I am considering the algebra of these QFT operators. And this algebra turns out to be a very well-studied algebra called a type 3 von Neumann algebra. Okay, and we are going to understand what is a type 3 von Neumann algebra. So let's spend a little time recalling some basic definitions of algebras. So what is an algebra? Okay, you all know what is a Hilbert space. you know that we have operators in the Hilbert space. I consider it could be a quantum mechanical system or a quantum field theory. Okay, then you consider only bounded operators on the Hilbert space. Bounded meaning that the norm is finite, and I just defined the norm. Okay. Now, a subset of S of all bounded operators on a Hilbert space. If you want, you can just think of operators in quantum mechanics and the Hilbert space in quantum mechanics. Okay, but we will do it for quantum fields. Okay, subset S of all bounded operators on a Hilbert space is an algebra if arbitrary linear combinations and products of operators in S are also in S. Okay, if this is true, then I call this subset an algebra. Now, if the adjoints of operators in S are also in the algebra, then I call it a star algebra. Okay. Now, S prime which is the commutant of the algebra S, is the set of all bounded operators that commute with every element of S. Okay, this set I call the commutant of the algebra. And a von Neumann algebra is a star algebra that equals its double commutant. So what is a double commutant? You take the commutant and you find its commutant. And if that equals the original subset S you started out with, then you call it a von Neumann algebra. Okay. Now, this is a basic result from quantum field theory, that the algebra of quantum fields in just the right exterior or the left exterior, doesn't matter. I'll take the right exterior, is a von Neumann algebra. Now, what is the commutant of this algebra? It would be the algebra of operators which commute with every element of the right exterior fields. Okay. And what would they be? They would be operators in the left exterior, which is the largest causally disconnected region from the right exterior. So here's a diagram which should explain these things to you. Let's look at the bottom diagram first. This is the black hole Penrose diagram. Okay. I have drawn the right exterior, which is the right diamond here. Algebra of fields in the right exterior I call S. Okay. Now you can see that any point in the left exterior, where I've called algebra S prime, that point is space-like separated from the right exterior. Okay, so there is no causal disconnection between the right and the left exteriors. So obviously, if you take a field which is localized in the left side, it will commute with a field which is localized on the right side because they are causally disconnected. Okay, so all the fields in the left side will commute with all the fields in the right side. So if you call the algebra of fields in the right side as S, the commutant will be S prime. And now let's go to the top diagram. Here I've drawn a general region in a general space-time. Okay, the diamond-shaped region is not in some black hole, it's in a general space-time. And let me say that the algebra of fields localized in S is called capital S. Then you can see that the left and right wedge regions, inside the left and right wedge regions, the points are space-like separated from the points inside the diamond region. Okay, so the field operators in the left region, in the left wedge region and the right wedge region commute with all the field operators inside S. Okay, so S prime here is the commutant of S. Okay, so now let's get, yes, question.
Sorry to interrupt you. So there is a question in the chat box.
Yeah,
asked
sure.
by Rajasmita.
Yeah.
So what do you mean by a bifurcation surface?
Okay, so I'm going to come to the bifurcation surface. The previous slides were just an outline of what I'm going to speak about. But let me point you the bifurcation surface in this diagram. So you look at the bottom Penrose diagram of the Schwarzschild black hole. You see these two lines which are crossing each other. At the center, you have a two-dimensional surface, which is called the bifurcation surface of the Schwarzschild black hole. And the Schwarzschild black hole has a time-lag killing vector, which will vanish on this bifurcation surface. So this is this two-sphere, which is at the center. This is what I call the bifurcation surface. But I will be coming back to it. So please just hold on with that question until when I explicitly show you the bifurcation surface. Okay. Right now, let's just try to understand basic algebras. Okay. I explained to you what's an algebra, what is a von Neumann algebra, and what is its commutant. Okay, so the right exterior algebra, the algebra of field operators in the right exterior of the black hole is actually a von Neumann algebra, as I just told you, but it's something called a type 3 von Neumann algebra in the classification of von Neumann algebras. So there is a classification. There are several types of these von Neumann algebras. And the classification is based on the different properties of each of the sets. Okay. Okay, so what are type 1 algebras? Type 1 algebras are most familiar to us because many quantum mechanical systems are described by these. Okay, so for example, if you have a system of finite qubits and you try to look at this operators in this particular quantum system, these will be a type 1 algebra. And what is the property of a type 1 algebra? Well, these algebras have density operators or density matrices, rho, both pure and mixed. Okay. And for all these density matrices, we can just show that rows, we can choose them so that trace rho is 1 using the usual Hilbert space trace. Okay, you know that for a density matrix, trace rho should be 1, and the trace is the usual Hilbert space trace. Now there is another type called the type 2 von Neumann algebra. In these algebras, we don't have pure density matrices, we have only mixed density operators. And the Hilbert space trace in these algebras is actually infinite. Okay, so I can never put trace rho equals 1 because the answer would be infinite. But what I have is what it is possible for me to do. It's possible for me to define a new modified trace, which I have labeled here by small tr, okay, as opposed to capital T and R in the previous case. And this trace satisfies the defining property of a trace, which is that trace AB equals trace BA. Okay. Now, using this trace, I can make my density matrix such that trace rho is 1. Okay. So I have such kind of renormalized density matrices in a type 2 von Neumann algebra. Now, what I can do, what is the advantage of having these types of density matrices? Well, the moment you have a density matrix, you can always write its von Neumann entropy as minus trace rho log rho. Okay. So both in the case of type 1 and type 2 algebras, I can define something like an entropy, okay, associated with the algebra. And this entropy is basically, of course, it will depend on the state of the fields. So that entropy would be minus trace rho log rho. So the dependence on the state is, of course, in rho. And then the entropy would be minus trace rho log. Now, the last kind and the most horrible kind of von Neumann algebras are type 3. In these algebras, we have no trace. That is, we have no finite trace which satisfies trace AB equals trace BA, and there are no renormalizable density operators. And it is a fact that if you take quantum field theory and you take quantum field operators in any subregion of spacetime, not the full spacetime, but only a subregion of spacetime, then that algebra is always type 3. Okay. So notice what is the important difference between type 1 and 2 and type 3. In type 1 and 2, I can define something called the entropy of the algebra. Okay, so this is the classification. And let us just now come to the main construction of Witten, which is something called a cross product. Okay, so let me tell you what is the motivation for that. In order to define the entropy for an algebra, we have just seen that it must be type 1 or type 2. Okay. Now, there is a mathematical construction which goes by the name cross product by the modular automorphism group. Okay, it's a very technical term. We will explain that soon. But what is the advantage of this construction? The construction is you can extend the original algebra. You can make it bigger by adding one more operator, such that the algebra now changes from type 3 to type 2. And so once I've extended the algebra, I can define an entropy for the algebra. Okay, so that's the advantage. So if I want to define entropy for the algebra of quantum fields in the right exterior, I can't do that straight away because it's type 3. But if I do this procedure to it and I extend it slightly, I can then define the entropy. Okay, so what is the procedure? The procedure is you enlarge the algebra by adding an operator. But this operator, new operator that you are adding, is not acting on the quantum field theory Hilbert space. Okay, it acts on a new Hilbert space, which you have to add to the original quantum field theory Hilbert space. So you have to take the tensor product of quantum field theory Hilbert space with this extra Hilbert space, and this new operator will act on that extra Hilbert space. Okay. And what is the operator you should add? So Witten's idea was that you consider a low energy kind of effective field theory of quantum gravity, which is just matter quantum field theories and gravitons. Okay, everything in the Schwarzschild background. Now, you know that this algebra, this is some quantum field theory in a sub-region of space-time. So it is, my sub-region is just the right exterior of the black hole. So that is type 3. Now I have to add one more operator, and you can't add a random operator, okay, in this procedure. If you want to change the algebra type from type 3 to type 2, you have to add a very specific operator, and I'm coming to that. So the specific operator which Witten proposed that you should add is the idiom Hamiltonian of the right side. Okay, so the right idiom Hamiltonian, HR. Now this HR is cannot actually be written as an operator H hat plus the left idiom Hamiltonian. Okay, so in the black hole, in the maximally extended black hole, you have both a left region and a right region. Now in the left asymptotic region and in the right asymptotic region, you can define two masses. One is called the idiom mass on the right, and another is the idiom Hamiltonian on the left. Okay? Now the two are related by this relation. You take this operator H hat, which is the integral over a full moment of time slice or a Cauchy surface of the time translation killing vector field of the black hole, Schwarzschild black hole, multiplied by T mu nu, which is the energy momentum tensor of the matter. Now this object, this integral, is actually the difference of the right idiom mass and the left idiom mass. Okay? So what I'm adding is to the right exterior algebra, the new operator I'm adding is the right idiom mass. Okay. Now this H hat operator is a very special operator called the modular Hamiltonian. Okay. Unfortunately, I don't have to, I'd have the time to get to modular theory, but I will tell you what is the special feature of something which is the modular Hamiltonian. Well, the special feature is, if I look at the algebra of the right exterior, let's say I have an operator A in the algebra of the right exterior. If I multiply the algebra on the left and on the right with these two terms, which is e to the I h hat s, and then e to the minus I h hat s on the right, where s is any real number. So if I do this, the result will still be in the algebra. Okay. So actually h hat is not a bounded operator. Therefore, it is not an operator in the right exterior algebra. But the point is, if you conjugate the field operator at the right with this h hat in this manner, okay, the result is in the algebra. This is a very important property called the modular automorphism. Automorphism because the algebra goes to itself under this transformation. And this only happens with the special operator h hat called the modular Hamiltonian. Okay? So that's the result, that it generates these automorphisms of the algebra. That means it takes the algebra to itself. Okay, so what was the construction, cross-product construction? It was adding a new operator and also adding a new Hilbert space portion on which that operator acts. So what am I going to do? I'm going to take my usual quantum field theory Hilbert space and I will tensor product it with the space of square integrable functions of the idiom Hamiltonian. Okay? So this is my new enlarged Hilbert space. You can either think of this extra piece as square integrable functions of the idiom Hamiltonian, or you can think of it as the square integrable functions of the conjugate variable to the idiom Hamiltonian. And the conjugate variable to the Hamiltonian is always the time. So this is a particular combination of the time on the left and on the right. Okay? I will not get into this. It's called the time shift, but it doesn't matter. You just think of it as time. Hamiltonian is always conjugate to the time. Okay, so you can think of this extra piece you have added as either square integrable functions of the Hamiltonian or square integrable functions of the conjugate time. Okay. So this is the product. This is the construction. You added the one extra operator and you added one extra Hilbert space on which that extra operator acts. Okay. Now this construction is called the cross product algebra. Okay, so mathematically, if I have to explain what I have just done, I have constructed an algebra generated by the following operators. A tensor identity, where A is any field, quantum field operator, and identity on the square integrable Hilbert space, which I've added. And I have also considered operators of the following kind: e to the is h hat tensor, e to the is h hat. Okay. Now, using these two types of operators, by taking products and linear combinations, I generate the entire algebra. Okay. Now, you have to prove that when you take products or when you take linear combinations of operators of this type, the result is also in the algebra. Okay. And this algebra closes The reason that this algebra closes is because of the special property of H hat that it generates automorphisms of the algebra. Okay? So because of this special property, it is true that this algebra, which is generated by these types of operators, closes. Okay? And this is the algebra I call the crossed product algebra. So effectively, although I have written a technical statement here, effectively, you remember that what we have done is we have added one more operator and we've added one more Hilbert space on which the operator acts. Okay. So this is my new cross product algebra, and the theorem in form norm and algebras tells me that the resultant algebra is type 2. Okay. And what is the feature of the type 2 algebra? It has a trace. Okay. This trace satisfies the property trace AB equals trace BA. It is not the usual Hilbert space trace, which may be infinite, but it's some kind of a renormalized version of that. Okay. Now, once I have this trace, what I can do is I can pick any state of the extended Hilbert space. Let me call that state phi hat. Okay. This is some state of the quantum fields and some state in the square integrable functions on square integrable functions of the ADM Hamiltonian. Okay. So you take this any state of the extended Hilbert space phi hat. Okay. Now you take any operator A, field operator A in your algebra, which you call A hat, and you define rho density matrix rho or rho phi hat by this equation. Okay. In this equation on the right, you can do the computation because you have the state of the system and you have the operator A hat. Okay. You can do expectation value of A hat in that state. In the left-hand side, I have given you what is the trace TR. Okay, this is some not Hilbert space trace, but some renormalized version of it. Okay, so from this formula, you can exactly determine rho phi hat. Everything else is known, so you can determine rho phi hat. Okay, so rho phi hat is now your renormalized density operator associated with the state phi hat. Now, the entropy of the algebra for the state phi hat is just minus trace rho phi log rho phi hat log rho phi hat. You can compute that. And this is the entropy of this algebra of the quantum fields in the right exterior. Okay? So you've defined an entropy of an algebra. Now let me explain to you, before I go to the next slide, let me just show you in this diagram. This is the Schwarzschild, extended Schwarzschild diagram. You can see that there are two diagonal lines which meet as a cross at the center. Every point in this diagram is a two-sphere, and these two cross lines meet at the center at a two-sphere, which I've drawn by a red dot. Okay, this is a special two-sphere on which the time-like Killing vector of the Schwarzschild spacetime vanishes. Okay, now this two-sphere is called the bifurcation surface, just to make precise. Okay, now what did these Witten and collaborators find? They found a very interesting result. They found that if you have semi-classical states phi hat, then the entropy of the algebra in the semi-classical state is the generalized entropy which Bekenstein defined, plus some constant, modulo constant, where the generalized entropy is evaluated at that bifurcation surface B, which I showed you in the previous diagram. Okay. So a semi-classical state, is not very hard to define. It is a state with small fluctuation in the conjugate variable to the ADM Hamiltonian. Okay, and that small, it is of order epsilon, where epsilon is a small number, and the result which I've just showed you is to leading order in epsilon. Okay, so you just you have added a new degree of freedom called the time, and that you don't want fluctuations in that to be very large. Okay, so you only take those states. So for such states, you find the beautiful expression that the entropy of the algebra of the fields, okay, the quantum fields, is equal to the generalized entropy of Bekenstein, modulo a constant. And this computation was done exactly in semi-classical gravity and explicitly used the semi-classical gravity equation that I showed in the first slide of the talk. And just to let you know what some result which we have done recently, what we showed was, all this was in Einstein gravity. What we showed was that if you take any arbitrary diffeomorphism invariant theory of gravity, then the same result is true, except the area of the horizon is replaced in the generalized entropy by the Wald entropy. Okay, I think there is a question here. Somebody
Yeah,
raised their hand.
yes.
Yeah.
Neeraj has a question. Yeah, Neeraj,
Yes.
you may go.
Hi. So this entropy which you calculated is
Hmm.
on the sub-region, like outside the horizon, right?
Yes, the right exterior. It is the
But
entropy of the algebra associated with the right exterior.
yeah. So in this case, why should it match with the generalized entropy? It should match with just the entropy of outside region, right?
No. So that is the whole point, right? This is some abstract algebra entropy. Okay. So I don't know what it should be. Some statistical quantity associated with algebra. But the point is you can show that it exactly matches with the generalized entropy, not the entanglement entropy of the exterior. You also get the area by 4G term.
Along with the, oh, all right.
Yes, you
So
get
it's
area by 4. So generalized entropy is what? Area by 4G plus the entanglement entropy. You get this combination.
one more question.
And you also should expect that, because in a sense, both entanglement entropy and the area by 4G term independently don't seem finite. Okay. But if you take the sum is expected to be finite. So the sum is well defined. Okay, so what you get from this entropy of the algebra, see, you don't know what to expect from the entropy of the algebra. This is like a statistical entropy associated to that algebra. But what you get, and this is a beautiful calculation, by using the semi-classical gravity equations, you can show that you get both the area term and you get the the entanglement entropy term. And why the bifurcation surface? Well, the thing is, the right exterior and the left exterior are joined to each other by the bifurcation surface. Okay, so when you just look at the right exterior, or when you just look at the left exterior, you also get the area by 4G term from the one point which is common to both of you.
all right. So if I'm understanding it right, then this uh, this is this entropy is of the whole region, not just the region outside the horizon, right? I mean, it's divided by the bifurcation surface, which is right at the middle. So it starts like the whole region is.
No. Wait. So what is entanglement entropy? In order to define entanglement entropy, I have to give an entangling surface to you. One side is called the interior, and the other side interior, or part one, and the other side is called part two. Now I have to, at any instant of time, I have to trace over the degrees of freedom on one side to get the reduced density matrix on the other side, right?
Agree.
So the entanglement entropy is that. So I trace over the left exterior.
Okay.
So that is, so if you're asking where that area by 4G term comes from, it is the one surface which is common to both the left and the right exterior, right? So when I trace over the right exterior, then I will get this area by 4G term.
Okay. Thank you.
Yeah.
Okay, Suneeta, I have a quick question.
Yes.
So when you just mentioned about this tracing over this density with this modified density operator, so you said that it's a renormalized version, right?
Exactly. Exactly.
So is it an assumption or is it guaranteed to be renormalizable?
No. It is renormalized because of the property of the type 2 von Neumann algebra. So I have done all this trouble to convert my von Neumann algebra from being type 3 to type 2, right? Now, once I have type 2, I'm guaranteed a renormalized trace. I'm guaranteed renormalized density matrices. So now what I do is I construct minus trace rho log rho for the renormalized density matrix. This is giving me some renormalized object, which I call the entropy of the algebra. This is a statistical quantity associated with algebra, right? The amazing thing is it turns out to be the generalized entropy.
Okay.
So on the left-hand side, the calculation has been done using this mathematical construction of converting to type 2 and then getting some renormalized trace and renormalized density matrix. On the right-hand side is where we are doing the tracing over the interior. The right-hand side, we have area by 4G plus entanglement entropy, where entanglement entropy is calculated at any instant of time by calling one part the outside and one part the inside, or one part system 2 and other part system 1, and tracing over one of them.
Okay, I see.
Okay.
So there is another question.
Suneeta, one more question. I'm Neeraj. I only typed that question, I guess, in the chat box. Can I ask?
Yeah, okay, go ahead.
Yeah. To convert it from type 3 to type 2, you
Hmm.
specifically used it by extended it by ADM mass, right?
Yes, yes,
ADM Hamiltonian, basically.
yes.
So, and you also mentioned that we can't use any random
No,
extension.
you cannot. You have to use the H hat operator is a modular Hamiltonian. That you have to use. If you don't use the modular Hamiltonian, then the theorem cannot be applied because the theorem says that to convert it from type 3 to type 2, you should exactly use the modular Hamiltonian. Okay, so the HR is what we added. HR is equal to H hat plus HL, and where H hat is the modular Hamiltonian, that is exactly required.
What do you mean by modular Hamiltonian?
So I have not explained that. I'm sorry. That's a lot of modular theory. It is a very specific operator, in the quantum field theory, and it satisfies some very specific properties. Okay, so I'm afraid I don't have the slides corresponding to that, and it's not easy to explain it in 5 minutes. But all I'm going to say is that it's a very specific operator. You cannot just add you can't add any operator and enlarge the Hilbert space for the space in which the operator acts. You can't do that randomly. You have to do it with a very specific operator called the modular Hamiltonian. The beauty is that in this case, the modular Hamiltonian, in the case of quantum fields in a Schwarzschild background, the modular Hamiltonian has a nice, relation to the ADM masses. It is the difference of the right and the left ADM masses.
Apart from all these
So
mathematical
if you want
implications,
to know more about this, please read something called Tomita-Takesaki theory.
okay,
That will
thank
tell you exactly what is the modular Hamiltonian.
Okay, I'm just giving my point here. So apart from all these mathematical intricacies, if I'm just using this ADM Hamiltonian, so apart from these quantum fields in the curved spacetime, I'm getting a hint that there should be something from the gravity sector.
Exactly, exactly. Now, but you know what? Since it's a very good point, let me just answer you. The thing is, there are also other constructions which people have done where they add the modular operator. In some other cases, the modular operator may not be this. This may not be the system you're considering. So people add an extra operator just as a regulator. So just to regulate this density matrix, in some other systems, people just add an extra modular operator and do the cross product construction and claim that it's just a way to regulate rho. So people have done that also, but the natural way in which it arises always involves gravity.
Thank you.
So there is one question in the chat box. What is the factor C? Could you please explain?
So C is a constant which is independent of state. It has a lot of terms in it. It's very complicated, but it's a constant independent of the state.
Okay, so there is one more raise hand.
Hello, ma'am. Sorry to interrupt you, sir. Ma'am, hello, ma'am. Ma'am, means C is we have added it explicitly, or
no. You when you compute the entropy of the algebra, see, entropy of the algebra is some statistical quantity you completed doing some mathematics, right? That's on the left. Then you can make the entropy of the algebra. You can combine all the terms in it to make it look like the generalized entropy, but you will have some state-independent constants, which I'm joining together. I'm lumping them into the constant C. Now you may ask, what is the use of this relation? Okay, that's what we'll see in the next slide.
Okay. Thanks a lot, ma'am.
Yeah.
Okay, so the extended Hilbert space is the tensor product of the quantum fields at the right sector of this bifurcation surface times the square integrable functions of the modular Hamiltonian.
Exactly, precisely. Not the modular Hamiltonian, the right Hamiltonian.
Right Hamiltonian.
So you can either think of them as square integrable functions of the right Hamiltonian, or you can think of them as square integrable functions of the conjugate variable, right? Like similar, just like in quantum mechanics, you think of psi as a function of p or x, right?
And that actually,
the conjugate variable is the time.
Right. So Parthoda has a question.
Yeah, sure, Parth. How are you, Partho?
He raised hand. I don't know.
Yeah,
whether
maybe he's left.
I mean, we may take up the questions later. You
Sure,
may go
sure.
ahead.
Yeah, sure. Let me complete. Okay, so what was the use of, okay, so I have some statistical entropy associated to the algebra. That's equal to generalized entropy plus a constant. That's also a constant here. So what is the use of this relation? Okay, the use of this relation comes from the nice property of the algebra entropy. Okay, the algebra entropy has a monotonicity property. Now, if you have a subalgebra B of a larger algebra A, and if you define the trace, so I have to just tell you that we have a renormalized trace in type 2 algebras. The trace is only defined up to an arbitrary constant, a multiplicative constant. So what you can do is, suppose you have a subalgebra B of A, and if you define the trace in such a way that you take an operator in capital B, which is called small b, its trace in the subalgebra B is equal to the trace of the operator in the full algebra A. So you can always scale your trace in such a way that this property is true. Now, if you have this property for the trace, then with the trace you compute the algebra entropy, then S algebra entropy of B will be greater than or equal to algebra entropy of A. Okay, so this is the monotonicity property, that algebra entropy is monotonic under inclusions B subset of A, which are trace preserved. Okay, this is a technical property of this algebra entropy. Now, what you can do is you can prove that S-gen of S-gen of the fields in the Schwarzschild background is actually always greater than or equal to 0. You can prove a version of the GSL that the generalized entropy at late times is greater than that at early times, precisely by using the monotonicity property of the algebra entropy. So this was the advantage. Okay, but in finding out that algebra entropy was a generalized entropy up to a constant. Okay? Constant doesn't matter in the actual proof, where you are proving that generalized entropy at late times is greater than that at early times. So this is the main application of this algebra. Okay? Now, it is true that there was a proof of the GSL, of the generalized second law, before all this, but that proof had some assumption that the various quantities like the rho, the density matrix, or other things are finite. Okay? They are not finite. So in the proof, it was stated that, if we have a renormalization scheme by which they become finite, then the proof is true. Now, what these people have done is to provide such a renormalization scheme. Okay? So everything is finite in this calculation. Okay, so if there are any questions on this particular generalized second law, I will take them now, because in the last few minutes that I have, I'm going to actually, I have about 10 minutes or 15, 10, do I have 10 minutes, Srijit? How much time do I have?
Yeah, I mean, you have 15 minutes almost. Okay,
great. So this is the main result which I have talked about in this talk. The next part is going to be an important conjecture in semi-classical gravity. So before I go to the conjecture, I want to ask if there is any more questions on this generalized second law. Okay, so I guess everyone has already asked their questions. So what we have done is we have seen a rigorous proof of the generalized second law using semi-classical gravity and using these new techniques from polynomial algebras. Now I will come to the next part of the talk, which has a conjecture. Okay, this is not yet proved, but is widely believed that it may be true. So this is an important open problem that, to prove in semi-classical gravity. And the conjecture is called the quantum focusing conjecture. It was proposed by these 4 people. Okay, so while the conjecture has not yet been proved, other results, that follow if it were true have been independently shown. Okay, so some results follow if this conjecture is true, and one of those results is something called the quantum null energy condition, which has been proven for several spacetimes to be true. So before I go to the conjecture, let me just recall some basic results from gravity, classical gravity. Okay, we have not yet gone to quantum fields. We're talking about classical gravity and classical matter. Now here is a cartoon sketch of a null hypersurface. Okay, we get null hypersurfaces all the time in classical gravity. Now, let me remind you of the interesting properties of a null hypersurface. The null hypersurface is always ruled. These blue lines are ruling the null hypersurface, and these blue lines are actually null geodesics. So null hypersurface is by null geodesics. Okay? Now, if I take the parameter along the null geodesic to be lambda, then, and if I take transverse coordinates to those blue lines to be coordinates y, then I can adapt, I can define a coordinate system on the null hypersurface using this lambda and using the transverse coordinates y. Okay. And the red line that I have drawn here is a slice of the null hypersurface. And the slice is given by the equation lambda equals v of y. Okay, so the slice I call the v of y slice. Basically, it is the surface which is given by lambda equals v of y, where lambda is the coordinate along the blue lines. Okay. Now, these blue lines are all null geodesics. Now, what is there is a quantity that you can define for these blue lines for this congruence of null geodesics, which are also all orthogonal to the null hypersurface. And the quantity that you can define is the classical expansion of the congruence. Okay. That expansion is denoted theta, and it is given by this formula. Limit a tends to 0, 1 by a, dA by d lambda. Lambda is exactly the lambda along these null geodesics. Okay. And what is A? A is the cross-sectional area. Now, you have cross-sections like the cross-section V of Y, which I have drawn here. The cross-sectional area is A. And this expansion measures how the cross-sectional area is changing as I move along the congruence. Okay. So, if this theta is positive, that means the cross-sectional area is increasing. If theta is negative, that means the cross-sectional area is decreasing. Okay. This is a classical quantity. Now, we know from Raychaudhuri equation, which is one of the most important equations concerning these geodesic congruences. We know from Raychaudhuri equation that if matter satisfies the null energy condition, then this particular inequality is always true. That is, d theta by d lambda is always less than or equal to 0. Okay. So in other words, if I start with a theta which was positive, it would get smaller and smaller. If I start with a theta which is negative, it would get more and more negative. Okay. So this is sometimes stated as the property that gravity tends to focus light rays. Okay. So what are my light rays here? My light rays are these null geodesics on this hypersurface. Okay. So the expansion along always satisfies the property that d theta by d lambda is less than or equal to 0. Now, the problem is that if my matter is a quantum field, then the matter does not satisfy this null energy condition. So this inequality d theta by d lambda less than or equal to 0 is not true in general. Okay, it's only true if matter satisfies the null energy condition, but quantum fields don't satisfy it. Okay? So for quantum fields in a space-time, the above inequality is not true. Now, this conjecture involves proposing something which is like a quantum version of this theta, and that's called the quantum expansion. And the algorithm by which you do that, roughly speaking, is that when you have classical matter, you know, for example, on a horizon that theta is always greater than or equal to 0. Okay. Now, in semi-classical gravity, where we have quantum fields, we know that the generalized entropy is always greater than or equal to 0. So the algorithm for converting these things into some quantum quantities is to replace area by generalized entropy. Okay. So I have to make it a little bit more clear, okay, what I mean by it. Okay, so now let's look at the diagram in the slide. Okay, in the slide, I have a Cauchy surface sigma. This is a moment in time slice of the space-time, which I have sigma. Now this is a in 4-dimensional space-time, a 3-dimensional hypersurface. So in that, let me take one point sigma, which is not really a point, it is a 2-dimensional surface. And this sigma splits this Cauchy surface into 2 parts. I will arbitrarily call one part as sigma in, and I will call the other part as sigma out. Okay. And I will construct the following quantity, which is S gen, which I call generalized entropy, but it's not of a black hole now. This is a quantity I'm defining for any Cauchy slice. Okay. So S gen is equal to area by 4g plus S out. Okay. Where area by 4g is the area of this surface sigma. Okay. S out is minus trace rho out log rho out, where I find rho out by tracing over the in degrees of freedom. That is tracing on the left-hand side. Okay. Now, this is my definition. I have defined something called a generalized entropy associated with the slice, which is given by this following formula. Okay. So I should just make my diagrams a little bit more, the diagrams will just get a little bit more involved. So you see that if I take this sigma, this red dot is my sigma, this is my 2 surface, which is dividing Cauchy slice into 2 pieces. This sigma, from this sigma, there are 2 orthogonal null directions. One is along the outgoing rays, what we call the outgoing null rays, and the other is along the ingoing null rays. Okay, so these 2 null directions define for me 2 null hypersurfaces. So I have drawn 1 null hypersurface here. So you also have something similar on the other side, but I'm not bothered. I've just drawn one particular null hypersurface here. So the sigma, this red dot, can be thought of as the intersection of the null hypersurface with the Cauchy slice. Okay, you see that the null hypersurface is intersecting the Cauchy slice at sigma. Now, here is the diagram on the right-hand side. Look at the diagram of the null hypersurface. Okay, it is given. So the sigma is like one slice of this null hypersurface. Okay, and that slice I call the V of y slice. Okay, which is the same diagram as I had here in the null hypersurface. So any slice of the null hypersurface is given by lambda equals V of y. Okay, so I will denote the slice of the null hypersurface, which gives me sigma as V of y. Okay. Now I can define the generalized entropy for this Cauchy surface exactly like what I have done here. The generalized entropy is a function of the slice that I have chosen because it depends on sigma, and sigma is depends on a particular slice V of y of the null hypersurface. So here I now tell you why I put V of y in the argument. Okay, this is a generalized entropy associated with this particular slice V of y. Okay. Now let's go back to this diagram. Okay, so here I have a slice V of y, which I have drawn on the right-hand side, the sigma slice, and which is given by lambda equals V of y. Now what I can do is I can deform this slice slightly. Okay, and I can deform it slightly at, say, the transverse point y1. And the deformation is given by the green curve here. Okay, so instead of the V of y slice, I have a V epsilon of y slice, where the epsilon is a slight deformation at the point y1. Okay. Now, if you look at the figure on the left, what happens to that figure? Well, under the deformation, come down to the last figure below. Okay, so I have my original slice capital sigma. I have my original 2 surface small sigma. Now, what I have done here is a deformation of the slice. So sigma has got deformed to another sigma prime, where the deformation is along the null direction k, which is given by the null hypersurface. Okay, so I have deformed sigma slightly along the null direction, and I get a new sigma prime, and I get a new sigma out prime, which is the Cauchy slice. Okay, so there is a new Cauchy slice, and there is a new surface sigma. Okay, this is the deformed slice sigma prime. Now, what will happen under this deformation? Well, of course, my generalized entropy, which I have defined for the particular slice, will change because the slice has changed. Okay, so I can define something called a quantum expansion theta at the point y1 to be the change in the generalized entropy because of the change in the slice at the point y1. Okay, and then there are some area factors here, 1 by root g y1. Okay. So what we have done basically is we have just taken the classical formula for the classical expansion and replaced area with the generalized entropy in this variation. Okay, so this is some quantity you can define. It is called the quantum expansion. Now you may tell me that instead of choosing this null direction, I could have chosen the other null direction. You can do exact constructions for all those cases. For all those cases, you will have a corresponding quantum expansion. Okay. And what is the quantum focusing conjecture? The quantum focusing conjecture is the conjecture that this particular inequality is true, which is that the change in the quantum expansion due to a change in the slice at some other point V2, okay, the change in the quantum expansion at V1 due to a change in the slice at other point V2 is always negative. Okay? And this Y2 can be the same as Y1 or it can be different. And this inequality, the quantum focusing conjecture says that this inequality is always true. Okay? This is like my analog of the fact that gravity always focuses. Okay, so and this is an analog of the classical statement I have from the Raychaudhuri equation that d of the classical expansion by d lambda is always negative. Okay, here I have something for the quantum expansion. So this is the quantum focusing conjecture. Now the thing to remember is it's
Suneeta, there is a question.
Sure.
He is asking that whether this formula holds for modified gravity.
So this formula, as it is proposed for Einstein gravity. Okay, it's not proposed for other theories of gravity. You can probably propose that, and someone may also someone may have already done that. But the point is that even for Einstein gravity, it's not proved yet. Okay, so this is an open conjecture in semi-classical gravity. This is really semi-classical gravity because we are taking quantum matter and we are taking the classical space. Okay, so I want to remind you that this is a non-local conjecture. You see, expansion, classical expansion, which comes in the Raychaudhuri equation, is local, but this is non-local because this involves generalized entropy. This is not just, area part. It is also the part which depends on the entire entanglement entropy of one side of the Cauchy slice with the other side of the Cauchy slice. So it's completely non-local. Okay. And I also want to say that in the initial paper in which these authors proposed this conjecture, they also proved the conjecture in the situation where Y1 is not equal to Y2. But the open problem is just the part where Y1 is equal to Y2. Okay, now what is the use of this conjecture? Well, it turns out that if this conjecture is true, okay, there's something else which is true, and that something else can be proved in other ways. And what is that something else? Now, it is well known that quantum fields do not obey the null energy condition. That is, if you take a null direction k, then the component tkk in the k direction, the null energy condition says that component should be greater than or equal to 0. But quantum fields do not obey this condition. Okay, but what you can do is, if the quantum focusing conjecture is true, then it implies that they obey the following condition, that the expectation value of tkk is in any state is greater than or equal to this particular constant multiplied by 2 derivatives of the entanglement entropy with respect to the lambda, with respect to the null direction, the same null direction which is coming in the component of T, of the energy momentum tensor. So this condition, this inequality replaces the null energy condition for quantum fields. Okay, and it is completely local. You know that there is also you probably also know that there's something called the average null energy condition, which is supposed to be true for quantum fields in many situations. And that is an averaged condition where you integrate the energy momentum tensor expectation value across a null geodesic or null curve. Okay. Now here I'm not doing that. That's a non-local condition. This is local. This is a local expectation for expectation value of tkk, which is greater than or equal to this term on the right-hand side. But the right-hand side can be negative. So that's the price you are paying for getting a local condition. Okay. Now, the quantum focusing conjecture implies this local condition. Okay. Now, the thing is, you notice that this particular condition for the energy momentum tensor does not have any Newton's constant in it. So although you got it from quantum focusing conjecture where you had an area by 4G term and all that, there is no Newton's constant in this inequality. Okay, and therefore it gives you hope that this might be proved using just techniques in quantum field theory. And it has been indeed done. In several spacetimes using QFT techniques, you can prove that this inequality is true. Okay, so this implies that the quantum focusing conjecture could also be true. Now, the new thing is, now the question you can ask is, can the quantum focusing conjecture be proved? And the new thing is, it may be able to prove it using recent developments in von Neumann algebras. Okay, not just the papers of Witten and collaborators, but further and subsequent papers where people have proved that for arbitrary subregions, the algebra entropy of that subregion is actually just the generalized entropy of that subregion plus a constant. Okay? So you may be able to use the properties of the algebra entropy to prove the quantum focusing conjecture. So that's where I will stop. Thank you.